In a quiet rehabilitation room, a patient who could not walk alone rises inside a metal frame, and suddenly the future looks human. This is not science fiction, because medical exoskeletons are already being used in hospitals and clinics for stroke, spinal cord injury, and other neurological recovery pathways. But the real story is not that a robot can move a leg. The real story is that these machines are trying to retrain the brain, challenge the body, and restore a piece of ordinary life that most people never think about. Standing up, shifting weight, taking one step, then another, can become a battle measured in millimeters. And that is exactly why exoskeletons matter, because they turn movement into therapy and therapy into possibility. What began as an engineering dream is now becoming one of the boldest tools in modern rehabilitation medicine. But to understand why these machines are so powerful, you first have to understand the problem they were built to fight. Every year, millions of people around the world face neurological injury or disease that steals movement from the body while leaving the mind, painfully aware of what has been lost. The World Health Organization says more than 15 million people are living with spinal cord injury globally, and rehabilitation is a core part of helping people regain independence. After stroke, traumatic injury, or neurological disease, even basic walking can become exhausting, unsafe, or impossible without support. Traditional rehabilitation can be effective, but it is labor-intensive, repetitive, and physically demanding for both the patient and the therapist. If a patient cannot produce enough safe, high-quality steps, recovery may be slower than it needs to be. That is where the exoskeleton changes the equation. Instead of asking injured muscles to do everything alone, the device adds powered movement, guided alignment, and repeatable stepping patterns. It is not replacing rehabilitation. It is intensifying it, standardizing it, and in some cases making standing and walking practice possible much earlier than before. And once you see that, the machine stops looking like a robot and starts looking like a bridge. A medical exoskeleton is basically a wearable robotic frame that attaches to the body and assists movement at specific joints. Most lower limb systems use motors at the hips and knees, while sensors track posture, angle, timing, and weight shift. Some devices respond to buttons or therapist controls, while others detect subtle body signals that indicate the user is trying to initiate a step. The result is a kind of shared walking, where human intent and machine precision have to stay in perfect conversation. That sounds elegant. In reality, it requires careful fitting, calibration, safety checks, and a huge amount of clinical judgment. Height, weight, joint range, injury level, spasticity, fatigue, and balance all shape whether a person can use a system safely. Then comes the software layer, where therapists can tune step length, speed, assistance, and progression over time. The exoskeleton is not just hardware strapped to a patient. It is a walking platform, a data platform, and increasingly a decision platform for rehabilitation. Several companies have pushed medical exoskeletons out of the lab and into real clinical workflows. Exobionics positions EksoNR as a neurorehabilitation exoskeleton for patients recovering from stroke, spinal cord injury, acquired brain injury, and more. The company says the system supports early mobilization and even includes pre-gait activities like balance work, weight shifting, and stepping in place. Indego therapy takes a modular approach and is used for standing and walking activities in patients recovering from spinal cord injury or stroke. LifeWord, formerly ReWalk Robotics, remains one of the most recognizable names because it helped bring powered exoskeleton walking into home and community use for spinal cord injury. In 2014, the FDA cleared the ReWalk personal system for home and community use, which marked a major moment for the field. In Europe, Wondercraft drew attention with Atalante X, A self-balancing rehabilitation exoskeleton designed for hands-free therapy. That hands-free capability matters because it opens the door to more natural upper body use, multidirectional movement, and more cognitively engaging rehab tasks. These machines may look similar from a distance. Up close, they reveal different philosophies about safety, user intent, therapist control, and what recovery should actually feel like. A real exoskeleton session does not begin with walking. It begins with straps, measurements, software settings, body checks, and careful communication between patient and therapist. Then the patient stands, often with a mix of fear, concentration, and disbelief. For some, the first goal is not distance. It is tolerance, posture, confidence, and the shock of seeing the world again from standing height. Step training follows, and every repetition gives clinicians a chance to reinforce alignment, rhythm, and controlled weight transfer. In some clinics, the machine also records performance data that can help show whether the patient is improving over multiple sessions. That feedback loop is one reason exoskeleton therapy feels different from old-school rehabilitation. It is physical, measurable, and deeply psychological at the same time. The promise of exoskeletons is powerful, but medicine is built on evidence, not applause. Recent studies and reviews suggest that robotic and wearable gait training can improve walking-related outcomes. Balance or lower limb function in selected patients after stroke or spinal cord injury. Some 2025 studies found wearable exoskeleton training produced outcomes comparable to conventional gait therapy, while other analyses reported gains in balance, strength, and functional scores. That may sound underwhelming until you remember what the machine is really doing. It is allowing safe, repeatable, high-dose practice in situations where manual therapy alone can be difficult to sustain. And in neurorehabilitation, repetition is not boring. Repetition is how damaged systems relearn patterns they once performed automatically. The evidence is encouraging, but it is also uneven because studies vary in device type, patient group, training intensity, and outcome measures. So the honest conclusion is not that exoskeletons are miracle cures. The honest conclusion is that they are becoming serious tools in a serious field, and the best results depend on matching the right device to the right patient at the right stage of recovery. For all their promise, medical exoskeletons still face hard limits. They are expensive, specialized, and far from universally available. They require trained staff, clinical protocols, maintenance, and patients who fit specific medical and physical criteria. They can also carry safety risks if used improperly, which is why regulatory oversight and controlled use matter so much. FDA recall notices linked to some ReWalk systems in past years are a reminder that this is still medical hardware, not magic. Even when everything works correctly, exoskeleton walking can be tiring, slow, and mentally demanding. And for many users, a wheelchair remains faster, more practical, and more empowering in daily life. That does not weaken the exoskeleton story. It makes it more honest, because the goal is not to replace every mobility tool, but to expand what rehabilitation and mobility can offer. The next generation of exoskeletons is chasing something much harder than walking. It is chasing natural walking, adaptive walking, and eventually walking that feels less like commanding a machine and more like recovering a lost instinct. Researchers are exploring lighter materials, smarter control systems, better balance, and tighter links between robotics, AI, and neurotechnology. Some European projects have even explored brain signal control concepts, trying to connect intention and movement more directly. Upper limb exoskeletons are also advancing, especially in post-stroke rehabilitation where arm and hand recovery can transform daily life. And the biggest shift may not be the robot itself. It may be the merging of robotics with data, remote monitoring, game-like engagement, and more personalized therapy design. In that world, the exoskeleton becomes less of a spectacle and more of a standard clinical instrument. Medical exoskeletons matter because they sit at the intersection of engineering, disability, hope, and healthcare inequality. They force a difficult question onto the modern world. If we can build a machine that helps people stand again, can we also build systems that make that help widely accessible? Because the technology alone is not the revolution. The revolution is what happens when technology, therapists' evidence, and patient determination finally move in the same direction. In the beginning of this story, a machine helped someone rise. By the end, you realize the more extraordinary thing was never the machine. It was the idea that recovery can be engineered, measured, and still remain deeply human. And that is why medical exoskeletons are not just about walking. They are about rewriting what the body can do after the moment everyone else thought the story was over.